YouTube live stream, let me just share my screen. Here, I'm gonna choose window and which one? Share. Oh, this one. Share. Okay. Now I should be live on both, and I hope there is no like sound issues anywhere. Okay. The scaling factors store how much they were scaled down. Okay, I want to go here and say, okay, actually, no, I want to go back to the same chat and say, explain this FP8 scaling, give examples, because to be quite frank with you, I don't quite get it. So let me just check my streams while this is, okay, we got LinkedIn, we got YouTube streams. Okay. Let me see here. Let's break down FP8 scaling with examples. Why is scaling necessary for FP8? So they, FP8, have very limited range and precision compared to FP32 or 16-bit floats. 16-bit floats. It's a float number in 16 bits. Okay. Yeah, I mean, yeah, we know that already, I guess. Okay. They can only represent numbers in a small interval around 0. Numbers with large magnitudes, example 10,000, or very small magnitudes, might fall outside its representable range. Why? I don't know. Yeah, maybe you just have 8 bits to represent. So you have how much? 256 or something possible represent numbers you can represent. Okay. They have fewer bits for the fraction mantissa, meaning they can represent numbers. They can't represent numbers as precisely. How many? Okay, let me just Google FP8 mantissa. Okay, let me just. Oh, wait, I need to mute my own stream. So this guy has one sign. So FP8 has one sign, 4 exponent, and 3 mantissa. We'll maybe see some examples. Let's see there. Just a second. Okay. If you directly convert a typical we're going to use this BrainFloat 16 tensor, like activations or weights, in a neural network to FP8, you'd likely encounter overflow, values larger than the maximum representable FP8 value. They become infinity. Okay. Underflow, values smaller than minimum representable positive FP8 values become 0. So I guess it can only represent, no. Yeah, so minimum value, like they should say maybe value closest to 0, because it also has sign. So I guess it can be minimum value from both sides of the negative and positive. Okay, let's see. Both overflow and underflow lead to significant loss of information, which harms the model performance. Okay. How scaling works? Scaling is a technique to map the values in your original tensor into the representable range of FP8 before the conversion. So we are mapping original values in original tensor to, so the original tensor is, for example, BF16, and we want to map them to FP8. Find the scaling factor for the given tensor T. You determine a scaling factor S. A common way is to choose S such that the largest absolute value in the scale tensor fits just within the maximum representable magnitude of the target FP8 format. Okay, so we want to find the largest value in the BF16 and get values. So that's going to be one end of the value we want to encode into FP8. Yeah, so that's going to be the largest value in the FP8 possible that we can encode. That's how we're going to scale it. Often S is max absolute of T divided by max representable FP8 value. Wait. What? Okay, maybe we'll see later. Scale down. Divide the original tensor T by the scaling factor. Scaling factor is just so maximum. Wait, doesn't make any sense. Okay, I'll ask you to show some examples later. Maybe we'll figure it out. But we have the scaling factor. So if we want to get T value, the value for FP8, then we just take the value from BF16 and scale it down by this scaling factor that I didn't quite get how they calculated it, but we'll see later. So that's how we convert from FP8 to BF16. Okay, let me just check my live. Okay. Now the values in T scale have a smaller magnitude and are more likely to fit within the FP8 range. So this is before we feed them into FP8. So this is like normalizing. Okay, so we'll understand it, but this is like scaling down just the values of the BF16 so they can later fit into FP8 representations. But we'll understand it better. Let's see. Convert to FP8. Convert the scale tensor to FP8. We have some function. So we give the scaled down tensor and we get the same tensor but in FP8. So we'll figure out how this works as well. Some precision loss might still occur due to the fewer mantissa bits. So it has 3 mantissa bits. Yeah. But catastrophic underflow is avoided for the most important values. Why most important? Why are they most important? Maybe, okay, so I'm guessing like biggest and lowest values are most important for some reason. I'm not sure. Store the scale. You must keep track of the original scaling factor, okay? Perform computation, the specialized hardware kernel, like torch scaled which actually I think we have it here. So this could be this scaled, or this, you see it's FP8. So we are converting this tensor, X tensor, which is activations, for example, and W is weights. So we do matmul between these two tensors. And I'm guessing we do that in FP8. So that's why I'm trying to understand how to convert to FP8. Okay, rescale during after computation. Oh, wait. So this torch scaled matmul takes the FP8 tensors, the two of them, and their original scaling factors as input. What? Takes the FP8 tensors. Why does it need to take scaling factors? I'm guessing like you're just gonna multiply these tensors. So why does it need scaling factors? Okay, well, we'll see later. So when we want to rescale during or after computation, the kernel effectively calculates scaling factor times this FP8 scale tensor, math multiplied. Oh, wait. So that's why we need these scaling factors. It's weird. It's weird. It's weird. It's weird. Let me remind myself what this scaling factor is. The original scaling factor. This is okay. Okay, we need to ask. I don't get this scaling factor that you apply before converting to FP8. So why are you scaling down 16-bit whatever? Okay, let me just, while this is generating, let me just check. Okay. Let's see. The confusion often arises because we think of 16-bit floats like BF16 or FP16 as already being low precision. Yeah, low precision, high precision. What do you mean low precision? I think they're high precision because they have they're very precise. However, the key difference isn't just the number of bits, but how those bits are allocated between range and precision. Specifically, concerning the exponent bits. Exponent bits, Mantissa, exponent bits, yeah, okay. Brain float sine 1 bit, exponent 8, Mantissa 7. So range has the same 8 exponent bits as FP32. This means brain float 16 can represent roughly the same range of numbers. Okay, because these are exponent bits, they determine how big number you can represent because they are the exponent. Okay, so you can have how many? 8 bits. 8 bits can represent 256 numbers, I'm guessing. So you can have a number that's some mantissa. Let me just check. Mantissa, let me just check. I guess you can have some number to maximum of 256. That's the exponent. Oh, what is this? Oh my god. Okay. Okay. So BF16 and FP32 have same exponent, can have same numbers, can represent same exponent. Okay, from very small to very large, approximately this number. It sacrifices precision, fewer mantissa bits, yeah, because mantissa is whatever you go up. So you got 0, or is it 1 dot and some numbers? So the more numbers you have after the dot, the more precise. And then you have times 2. I don't know. Oh my god. Anyway, what's important is then, I guess, bigger exponent can represent bigger number, and mantissa can represent more precise number. That's what we need to know. Okay, so FP8, so specifically exponent 4 mantissa 3 variant, and then you have sine 1. So 1 sine, 4 of exponent, 3 of mantissa. Variant used here, yeah, is this shown somewhere? Let me just copy this and see if this is present in this code that we are reviewing. Yeah, it is here. Okay, so it's converting. What is this? This is the input. No, this is scaling. This is so confusing. Is this scaling factor of x tensor? It's tough. Okay, sine 1 bit, exponent 4 bits, mantissa 3 bits. Okay, range has only 4 exponent bits, so FP8 has only 4 exponent bits. This drastically reduces the range of numbers it can represent compared to 16 or 32 bits. The maximum range value is much smaller, around 448, according to NVIDIA docs. Okay, let me ask it a question. Why 448? Don't you have 2 to the power of, so we have 4 exponents, so it's going to be 2, 4, 8, 16 as max exponent. Let me just see, like, if you don't understand what I asked, it's okay, I don't understand either. Let's see what it's going to say. Let's see. It's going to type. Oh, let me check my streams and stuff. Okay. Oh, this is typing for a long time. You're right to question that. Okay. The number of exponent bits doesn't directly translate to 2 to the power of that number as the maximum value representable. Okay. So I was saying, like, we have 4 exponents, so you can represent in 4 bits, you can represent like 2, 4, 8, 16 numbers. 16 numbers. It's a bit more involved due to how floating point numbers work. Here's the breakdown of FP8 exponent 4 mantissa 3 exponent bits, 4 bits. These bits represent a range of exponents, typically powers of 2. These bits represent a range of exponents. What is a range of exponents? Typically powers of 2. Okay, so these 4 bits just tells you from, like, what's the minimum and maximum number of exponents you can have and everything in between. So that's what they mean, like, this is a range of exponents, yeah, these 4 bits. Typically powers of 2. With 4 bits, you have 16 possible patterns from 0, 0, 0, 0 to 1, 1. Okay. Exponent bias. These patterns don't directly map to exponents 0 to 15. They are interpreted relative to a bias. The bias allows the format to represent both very small negative exponents. We have different formats, so we don't necessarily just use exponents to encode numbers from 1 to 16, or from 0 to 15, I should say. But we're going to use it to encode higher range of numbers. Yeah, we can just encode 16 numbers. So we're going to maybe encode like different numbers, not just like these lame 0 to 15. Because we can only represent 16 numbers, so we need to be smart how which numbers we represent, I guess. So that's in FP8 exponent. So we're talking about exponent in FP8. Okay, let me check real quick. Okay. The bias allows the format to represent both very small negative exponents. Yeah, negative exponent means it's between 0 and 1. When you exponentiate it, you're going to get number between 0 and 1. And larger positive exponents numbers. For an n-bit exponent, a common bias is 2 to the power of n minus 1. What? Minus what? What? The bias is 7. Okay, so we have some random formula that's like, take the number 2, power, number of bits, which is 4 minus 1, and then minus 1. So I guess we get this like bias 7 for some reason. Why is this formula applied? I don't know. And what is this bias even doing? Reserved patterns. Not all 16 patterns represent normal numbers, typically. Typically, 0, 0, 0 is reserved for representing 0 and subnormal numbers. Very tiny number. What do you mean? What? 1, 1, 1, 1 is often reserved for representing infinity and not a number. How can one thing represent two things? I don't understand. Calculating max exponent. The patterns for normal numbers range from 1 to 14, but in binary. So we have from 1 to 14 to encode these things, to use. That's a crazy low amount of numbers we have. That's crazy how few numbers we can have in like FP8. That's crazy. How do they train whole neural network with just like a few numbers? Okay, I need to ask this. Let me Google how many numbers can FP8 represent? It seems like a very small one. 256 possible values. But we can, like, it doesn't need to be like from 0 to 255 numbers. We can represent any number. That's great. So the whole DeepSeek is trained using 256 numbers, and that's it. that's crazy. Calculating, what is this? Calculating max exponent. I read this already. To get the actual exponent value, you subtract the bias. Smallest normal exponent, from -6 to +7. Largest normal exponent. I wonder why they call it normal. Okay, so we go just the minimum maximum binary value we can encode minus the bias. So now we want to represent numbers from -6 to +7. So are these so I'm guessing these are exponents that we want to represent, which kind of makes sense. Maybe you don't need higher than 2 to the 7. So largest power of 2, the exponent can represent for normal numbers is 2 to the 7. Okay, let's check mantissa bits. So we got 3 bits here. Okay, I think this is pretty clear though. So when we talk about exponent, 2 to the power of something, if we just had positive numbers, then we would never get a number between 0 and 1 in our neural network, but we want those numbers as well. So I guess we want to somehow shift exponents from just positive numbers to also include negative numbers, so we can get values from even like small values, like from 0 and 1 to 1. Because negative exponent will give you value between 0 and 1. Okay. Mantissa bits, 3 bits. These bits represent the fractional part of the number. Yeah, fraction, yeah. So we go 0 point, and then whatever numbers we got behind the decimal dot, those are mantissas. So we just have 3 bits. So we can represent numbers like 1, 2, 3, 4, 5, 6, 7, 8, and that's it, 8 numbers. And yeah, from 0 to 7, I'm guessing. Okay. For normal numbers, there is an implicit leading one. So it's 1 point, it's 1 point and then mantissa, not 0 point and then mantissa. So this is what it should look like. So we have 1 point and then mantissa should be some numbers times 2 to the power of exponent. So an exponent can be from -6 to 7. So this is how you're going to represent numbers. So I guess we have only 3 bits. 3 bits can represent numbers. Wait. That's crazy again. Is it only possible to put a single number here in Mantissa? And that single number is between 0 and 6, because you just have 3 bits. So, wait. So I'm guessing like you can only have a single number in Mantissa because it's 3 bits. And then, so how would you encode this number? So this is a number that's like equal to something. I don't know what. This is an actual number that you get when you calculate it. So how do you encode this number? So we would encode this number 2. This is Mantissa. So you would always have 1 point, and then we need to encode this. That's going to be 0. No, it's going to be 1 0. But 0 1 0 because we are encoding it with 3 bits. We also have sign here. So this is plus sign. So that's going to be number 0, or 0. So we got plus sign. Number 2 is the Mantissa, and -6. So we're going to encode -6 by this formula up there. So it's going to be 0001. 00. So that's going to be our FP8 number. That's going to encode this number. Okay, I think I'm getting it. Let's go. Okay. Checking my streams. Okay, we got some viewers, likes. Let's go. Okay. Okay, let's go. Calculating max normal value. The maximum value. Oh, wait. Did we go through this? No. Mantissa. So the significant. Is it a mistake to spell like this? The precision part. It's significant. It's not a mistake. This is the name of this precision part. Wait, no. It's name of this whole thing, significant. So this fraction is also Mantissa, I'm guessing. Fraction is encoded as this Mantissa that I explained. It's 0 1 0 in our. Okay. With 3 bits for the fraction, the maximum fraction value is 111, which is 7. 111 is 7, but if you have 0.111, this number is then 0.875. Okay, I don't know if this is correct. I think it is. I mean, it must be. Let me just close my window like this. Okay. I hope it's right. Let's see later. Let's see. Maximum significant 1 plus this. Why did it say minimum 0 and maximum 1? Why? I don't know. Calculating max normal value is going to be max significant times 2 to the max exponent. Maximum, let me calculate it. So maximum significant can be 0.875 and maximum exponent is 7. I thought maximum significant would be this. So that would be 1.7, which is not it. Okay. It is what it is. Maybe we'll figure it out. Okay. The maximum value is approximately, okay, we already read that. maximum number you can encode in FP8 would be 240 in our range that we created here. Okay, where does 448 come from if we have 240 as maximum value? Okay, so few potential areas. Specific FP8 variants, the type used in Torch FP8, this guy that we are using here. The FN suffix often implies a variant that doesn't have dedicated non-infinity patterns. Really? Okay. Instead of 1111, exponent pattern might be used to represent the largest possible finite exponent. If the bias is 7, this pattern, 15, would give an exponent of 8. In this case, we get 480 as the maximum number. This is closer, but still not 448. Okay. I mean, I think I understand now where this number comes from, by the way. Practical scaling choice. Most importantly, look at the code itself. Casted linear, use FP8 true, model dimension, root of model dimension over 448 for some reason. And then this is scaling factor of it's 24 over this. These seem to be random numbers because I don't understand them, but let's see. Appears, so the number 448 appears explicitly in the scaling factor chosen by the developer for the LLM head layer. I wonder who the developer for the LLM head layer is, by the way. I'm guessing it should be NanoGPT or even Andrei Karpathy or some, I don't know. Okay, this strongly suggests that 448 is not necessarily the absolute theoretical maximum of the exponent for Mantissa 3FN. Okay, but rather the target value of reference point used for calculating the scaling factor in this specific implementation. The developer might have chosen this based on empirical observation of the maximum absolute values encountered in activations or weights for that layer during typical training runs. Okay, so you just tried a bunch of values and find this was the best. A desire to leave some headroom below the absolute maximum value. Okay, leaving some, not choosing the maximum. Okay, it's even more confusing, but standardization within their project or based on recommendations from NVIDIA or Hopper architecture, I'm guessing. Okay, I want to ask, let's give some examples in FP or let's say BF16 and convert them to FP8. Draw matrices and tensors or whatever examples you are giving. Okay. Let's see. The stream is running for this 127 on YouTube. It's a little, actually YouTube stream is 34 minutes. What? Yo, I started LinkedIn stream before YouTube and YouTube is running for 34 minutes. What? How does that make any sense? Yo, LinkedIn stream is so behind. Bros are watching like 15 minutes ago. That's crazy. I wonder if it's gonna have some lags and stuff. Okay, let's check this. So let's illustrate the BF16 to FP8 conversion with scaling using the value 448 as our practical maximum target magnitude based on, okay, whatever. Input tensor BF16 in BF16, targets tensors in FP8. Reference max magnitude will scale so that the largest absolute value in the input tensor gets mapped to at most 448. Yeah, this is because we are taking FP8 range such that the maximum value in this range is 448, because we can represent just 256 different numbers in FP8. So we want to choose which ones carefully. So we're going to take, for example, this. I'm guessing like this number is the maximum number we would have in our tensor, BF16 tensor. It's confusing. It's confusing for me as well. Let's see further. Tensors with values initially smaller than 448. Let's say we have a BF16 tensor A. So it has these values: 10, minus 50, 200, minus 15, 0.5, and minus 300, okay? Find maximum value, but absolute maximum value. So 300. Calculate scaling factor. Since 300 is already less than this guy, we could use a scale of 1, okay? However, often a scale is calculated anyways for consistency, or perhaps a predetermined scale is used. Let's calculate it based on the principle. So right now we are trying to scale down this vector, so the maximum value in this vector is no higher than the maximum value we can represent in FP8. So if this vector had like 1,000, but the maximum value we can represent in our FP8 is 448, then we need to scale down the whole tensor so that biggest value in tensor is this. Okay, let's see. Let's calculate it based on the principle. Scaling for this A is going to be maximum of absolute of A, so it's going to be 300 divided by this maximum value we can represent with FP8. So that's the scaling factor. So I'm guessing now we want to divide each of these numbers or multiply, because if we divide, we're going to make them bigger because this number is below, like between 0 and 1. Wait, let's see. In practice, scaling might be adjusted to powers of 2 in or other specific values, but we'll use this calculated value. Scaling might be, okay, whatever. Let's use scaling A to be 1. Didn't he just calculate this scaling? Why did he even calculate it then? Here, for simplicity, as no value exceeds the threshold is going to be 448 for these values. Okay, okay. Scale down. A scale down. Yeah, we just divide A by the scaling factor. Since yeah, scaling factor is 1, so it's going to stay the same. Let me just check. Okay. Wait. Okay. Convert to FP8 E4M3. Now convert A scaled to FP8. Since FP8 has only 3 mantissa bits, it's exponent 4 mantissa 3. Some precision loss is likely. I'll explain this, don't worry. Especially for numbers that aren't the exact sum of powers of 2 multiplied by exponent. What? Okay, we'll see. So we have 10, minus 50, and 200. Those are values might be represented exactly or very close. Is it these values, do you mean? Let's see what the other comment says. 0.5 is 1 to the power of minus 1, often exactly representable. Okay. 2 to the power of minus 1. Exact representation depends on the specific FP8 implementation. Minor rounding might occur. Yeah, that's because FP8 can only represent 256 numbers. And then whatever numbers you choose, there can also be some numbers that are not representable. Okay, so we store our scaling factor. Example 2. Okay, well, this was one example, I guess. Tensor with the values exceeding, so we have 600. Now, scaling factor is going to be maximum, so 600 divided by our maximum value we can use in FP, representing FP8. That's our scaling factor. So I guess now we divide. Okay. Okay. So now we scale down all of these. Oh wait, this was the absolute maximum. Okay, never mind. 800. So now we scale down. Now we get this scale down BF16 tensor. Okay. And the maximum value here is representable with our 448. It has minus, but that's okay because we have one sign bit in the FP8. We will represent it easily. Notice that the largest absolute value is now just below our target. Okay, so it's representable. Convert to FP8. Okay, so convert B scale, so the new scaled tensor. Values will be rounded to the nearest representable FP8 number. Minus 4479. Might be clamped to or rounded to the closest value, potentially this one. Yeah, or slightly less y. No, it's going to be, yeah, that depends on what we are representing with our. So we are still not sure that we are going to use 448 as like maximum and minimum. I think we are sure. Why slightly less? I don't know. We'll figure it out. Depending on the exact E4M3 range and rounding. Yeah, depending on how we choose and rounding as well. So maybe we will not get this number exactly. Maybe some similar number or something. Now they rounded this for some. Why did they round this immediately? I guess you wouldn't be rounding this until you know which FP8 version you are using. Which numbers, I mean, you are representing. So I guess you would just take whichever numbers you are representing here and map or convert these to the closest numbers in whichever numbers you are representing here. So I guess rounded clamped to nearest representable, potentially maxed negative. I guess they are all like just put to the nearest represented in the FP8. And we store this scaling factor for later for some reason. I don't know why. Okay, my OBS running well. Example 3. Okay, example 3. Tensor with mixed magnitudes. What? consider this tensor. Maximum absolute is 950. So the scaling factor is 2.12. And then we scale down, I guess. So this is a bit larger than our maximum representable. That's okay, because we will just like get this to the nearest representable number, which is minus 448 in our case. Okay, convert. Note how small value 0.1 becomes even smaller, 0.047. Yeah. When we are scaling down. Okay. And might lose significant precision or even becomes, yeah, that's because maybe such small value, maybe it's more sensitive to like changing its value. I don't know. Might lose significant precision or even become 0.0. Yeah, maybe value is like very small compared to other values. Okay. In FP8, if it falls below the smallest representable positive value, underflow. So the smallest so this is the largest negative will likely be clamped to the maximum represent. Okay, well, this is different example, but we are talking here. It might lose significant precision or even become 0 if it falls below the smallest representable positive value. Yeah, that's the problem. The smallest representable positive value. Now it's gonna get clamped onto like, if we are representing 0 or the whatever is the smallest one. So that can be big. Okay, how do we deal with this? I don't know. Maybe we just ignore it. Okay. Okay. I mean, I understood this, I guess. Okay, I guess let's continue with our code thing. Torch. Okay, now I'm gonna copy all of this, add to chat, and explain. Okay. I'm checking my live streams and stuff. We got some viewers, both YouTube and LinkedIn. Anyways, let's go. Why is it taking so long? Where's my, is it my internet? Let me check my internet. It works. Yeah, it works. Let me just rerun this, I guess. So looking at this, we have X tensor, W tensor scaling that we calculated earlier. So this scaling, we are scaling maximum value of the BF16 tensor to be the maximum to become. So we are reducing it and all of the other values by a scaling factor, so that the maximum value in the BF16 becomes maximum representable value in BF8 or FP8. Why is this not working, bro? Maybe it's maybe my subscription just expired. Okay, let me try here. Just add to chat and explain. Let me also try in a different, like ChatGPT directly. I can read it for you. Okay. Okay, so yeah, we got this customly implemented matmul. The goal of this operation is to perform quantized matrix multiplication. So that's quantization, converting BF16 to FP8. Yeah. Okay. using this format, which is defined here, float 8, FP8, exponent format is 3, and FN means like custom implementation or something, I don't know. And then return the result of the matrix multiplication, BF16. So we get imp. Whoa. How? No, it's no. Wait. It says that it will return scaled up, so FP16 result. So are we just doing matmul? So in with the quantized, and then scaling it back to FP16. Okay, so we have scaled matmul. So we got FP8 and this transposed matrix FP8. And then output type is BF16. I guess it does the matmul with this smaller type and outputs in BF16. And we are sending in scale. So scale for A. Scale. So this is gonna help it convert from the FP8 from to BF16 because we scaled down the numbers earlier. So it's gonna be x.new tensor. It's weird. I think what it does here is it says like don't modify, like it creates new tensors so they don't get modified in place or something. I don't know why this thing is not working. Maybe we'll fix it somehow. Let me see what ChatGPT said. It was everything I said until now. ChatGPT kind of repeats. So let me see if I can see explain. Okay, it works here. Ensure the both input tensors x and w are contiguous in memory. I forgot what it means. This is important for performance reasons as contiguous tensors allow for more efficient memory access patterns. It didn't even explain what it is. What is contiguous? Whatever. What does it mean? Contiguous tensors are stored in an unbroken block of memory, which allows for efficient memory access pattern during operations. Yeah, this is crucial for performance reasons, ensuring that both input tensor x and w are contiguous in memory. Okay, let me check here. So this guy ensures memory layout is compatible with lower level operations for performance reasons. What? Memory layout is I don't know. Okay, explain. Convert this useless, I'm gonna hide it. Convert the input tensor x to a lower precision format by scaling it with this. No, it's not by scaling it with this. It's after scaling it, because you first need to scale to the maximum representable now. Okay, I explained it, so maybe you can rewatch if you don't know what this is. This scaling is done to adjust the range of values to fit within the representable range of float 8. Yeah, the division, I guess, method divides each element of x by the scale factor and converts the result to FP8. Yo, so easy. Okay, so we get the big FP16, BF16 tensor, scale it down with the scale factor, and convert to FP8. So easy. Okay, so easy after I've been reading this, understanding it for an hour. Okay, I guess this does the same thing. Okay, what is this? We got scaled mat multiply, we give it these two, okay. Output type, I already said this. Let me see what ChatGPT says. Divide by scale, okay, what is this? Transpose, we already know that. The original scales are passed back to the quantized the result immediately. Yeah, I mean, that's it. We understand what this does. Okay, we understand this function. Okay. What is this impl? This is a torch compile. It's gonna compile. We understand this, I think. I just want to check if Evin wrote some kind of custom kernels or something. I remember that being somewhere, but now I don't see it for some reason. Anyways, okay, let's go to the next function. What is this? This is just to ensure, like, to prevent bugs. You need to check if both all tensors are on the same device. That's a weird name for the function. And why does it have this same like MMOP, which is here? What is this? Okay, let me ask ChatGPT. Chat. So weird. So explain this lower fake function with comments. Ensure, okay, but explain the at mmop dot register fake and why does it have this as name and how does it relate to the upper function? Okay, submitted it. Okay, this mmop register fake decorator registers this function as a fake implementation of the mmop custom operation. And that's gonna, okay, let me just accept. So mmop custom, what? This is typically used for testing or simulation purposes where the actual operation might not be available or needed. Okay. So this is just for testing. So this is not like to check if this whole file is going to run properly by ensuring everything is on the same. This is just for testing. Okay. The function name underscore, underline, whatever, is used here as a convention to indicate that the function is not intended to be called directly by name. It serves as an anonymous or placeholder function name, which is common in Python when the function's name is not important. Ensure both X and W tensors are two-dimensional. Okay. They have like these same shapes, I guess, because you need to mat move them by this shape. But this is important. Perform mat move, but transpose this, okay. And then, what? Convert X and W to a lower precision format float FP8 for potential efficiency gains. Okay. Let's go to this one. I want to copy it. Why is my thing not? Maybe ChatGPT is not working. Let me try this guy and ask and say, explain. So weird. Why is it not working? Anyways, okay, I can go ahead and tell it to comment out this with the edit. So explain in comments. Define a custom operation for the backward pass of a matrix multiplication in the NanoGPT library. That's gonna be tough to understand maybe. Let's see. Okay. Wait. We got use torch compile to optimize the implementation. Okay. I don't like it in these comments to the side because it might mess something up. Okay, this is just another custom operation and backwards. Sure, this so gradient is like tensor, okay. X and W. Convert scaling factors to tensors with float 32 precision for accurate scaling. What? Scale the gradient tensor and convert it to a lower precision format. Okay, scale down and convert to FP8. We already had this. Compute the gradient with respect to the input tensor 8. Let's see. Use the scaled matrix multiplication with the transposed weight tensor. Stuff. Okay, scaled towards a scaled math. Okay, so this is native function. These are gradients. What is grad FP8? What is this grad even? Grad S. It's crazy. It's crazy. What is this grad? Where is it coming from? Where is this coming from? I don't know. We'll figure it out. Okay. Ensure the weight tensor is contiguous after transposing. So it's one chunk in memory, not separated in memory. Specify output data type for the result. Okay. Scale A, scaling factor for the gradient tensor. What? Scaling factor for the gradient tensor. But why is it scale A? Whatever. Scaling factor for the weight tensor. Ah. Okay. And why do we have this like inverted scaling? It doesn't make it, I don't understand. Use fast accumulation. Disable fast accumulation for precise computation. Okay. I just don't get why is it inverse here. So grad new tensor. Okay, I need it. I need to ask it like, what is this? What is this and what is this grad? And keep comments in lines above the code line and not in it. Okay. I said not in it, but whatever. Convert scaling factor to tensor with f float 32%. Okay, we already got this. Grad.new tensor is used to create a new tensor on the same device as grad. Easy. Same device as grad. That's crazy. Ensure the gradient tensor is contiguous in memory. I'm just wondering, like, where does this gradient tensor come from? So we got this we are calling it from where? Here. So this is G. Okay, G. This is the gradient. Okay, let me accept this. Let me find this guy. I will find you. Okay. It's not here. It doesn't make any sense, bro. Okay, let me. MM backward. Maybe that's what the name of the function we are defining. Yeah. Yeah, we are passing gradient here in define backward. I still don't know. I want to see where this gradient comes from. Does my ChatGPT work thing? Explain where gradient comes from. That's crazy. Maybe if I try letting it auto choose. Explain this grad. Maybe I need to restart my IDE cursor. Okay, I think we understand this. I think we get it. We get it. Execute implementation function with the provided gradient and tensors. Return the computed gradients for the input and weight tensors. Let me just check my streams here. Okay. My LinkedIn stream is so behind. It's like 25 minutes behind. Why? I don't understand. Whatever. Let's see. Okay, guys, I think I'm gonna make a pause here. Like, I've been trying to understand this for an hour. So I will maybe stream a bit later, or you can get some notifications. Maybe I'll stream in an hour or something, or you can just check later, I guess. I don't know when. So maybe see you in the next stream a bit later. Bye-bye.